Welcome back. In our last explainers, we talked about building good arguments and spotting bad ones. While today, we're taking that idea to the absolute extreme. We're going to dive into how mathematicians tried to create the most perfect, totally unbreakable arguments you can imagine using nothing but the language of pure logic. So let me ask you this, and it's a big one. Can mathematics ever be wrong? I mean, can we be absolutely certain that its foundations are perfect, with zero contradictions? You know, about a century ago, that very question kicked off a huge revolution. The smartest people around basically set out on a quest to prove, once and for all, that math was built on solid rock. So to figure that out, we're going to follow the incredible story of mathematical logic. First, we'll look at the dream of a perfect language for math. Then, we'll see the crisis that almost blew it all up. After that, we'll explore the amazing tools they invented to put it all back together. And this is where it gets really wild. We'll uncover a shocking truth about what we can even know. And finally, we'll see how this whole abstract adventure ended up building the very world we live in today. Okay, so let's set the scene. We're in the 19th century. For like thousands of years, everyone just assumed that things like geometry, based on Euclid's axioms, were totally unshakably true. But then mathematicians started poking at it and found some, cracks. They realized that some of the most basic assumptions, like the famous parallel postulate, couldn't actually be proven from the other rules. This was a huge deal. It really shook their confidence and kicked off this massive quest for real, provable certainty. So in response to this, you get these pioneers, guys like Boole, Frege, and Peano, and they start this incredibly ambitious project. Their goal? To rebuild all of mathematics from the ground up, on a foundation of pure symbolic logic, a language with no fuzzy human intuition, no ambiguity. And right around the same time, this guy, George Cantor, comes along and just blows everyone's minds with his work on infinity, like showing there are different sizes of infinity. It really seemed like they'd done it. It looked like they had found a brand new, perfect foundation for everything. And that new foundation, it really looked like it was going to be Cantor's set theory. I mean, it's the study of collections of objects, right? It was so powerful that everything in math, numbers, shapes, you name it, could be defined as some kind of set. It was perfect. But just as they were building this beautiful new mathematical paradise, a simple little question popped up. A question so devastating it threatened to bring the whole thing crashing down. So, in 1901, a philosopher and logician named Bertrand Russell comes up with this. And you really got to think about this for a second. If the set contains itself, well, then it breaks its own rule, so it shouldn't contain itself. But wait, if it doesn't contain itself, then it fits the rule perfectly, so it should be in the set. It's a total, complete contradiction, a real brain breaker. And look, this wasn't just some clever little party trick or a riddle. This was a bombshell. It proved that the very language they were using to build certainty, what we now call naive set theory, was broken. It was logically inconsistent. The whole grand project, this dream of a perfect, unbreakable mathematics, it was suddenly on the verge of collapse. But here's the thing about mathematicians. Faced with a crisis that would make most people just give up, they didn't. Instead, they did what they do best. They got to work. They invented. They developed this incredible new set of tools, basically creating 4 whole new fields of mathematical logic, all designed to analyze the problem and rebuild math on much, much safer ground. Okay, so tool number 1, they didn't just throw out set theory. No, they fixed it, they beefed it up with a bunch of strict new rules and axioms. You might hear the name Zermelo-Fraenkel. And these rules were specifically designed to make sure a paradox like Russell's could never even be written down. This patched-up version became the new, much more stable, official language of mathematics. All right, so once they had a safer language, the next obvious question was, okay, what do all these symbols on the page actually mean? And that's where model theory comes in. You can think of it like a bridge. On one side, you have the formal language of logic. On the other, you have all the actual mathematical worlds or structures. Model theory is the field that studies that connection. It asks, what kind of worlds make our logical sentences true? Next up, number 3, recursion theory. And you'll also hear this called computability theory, which is maybe a bit more descriptive. This branch asks a really, really important question. What problems can actually be solved by a machine? With a step-by-step procedure and algorithm. This field is all about figuring out the absolute limits of what is and isn't computable. And last but not least, we have proof theory. Now, this is where things get really meta. Instead of just using a proof to show that something is true, this field takes a step back and studies the proofs themselves. It treats proofs like they're mathematical objects, so you can analyze their structure, their properties, and, this is the key part, their built-in limitations. So here's a great way to think about it. You've got these 4 new fields, all born from that one crisis, and each one is asking a different fundamental question. Set theory asks, what stuff even exists in math? Model theory asks, what do our statements about that stuff mean? Recursion theory asks, what problems can we actually solve? And proof theory asks, what can we even prove? Each one gives us a totally unique way to look at what mathematics really is. Okay, so now they've got this incredible new toolkit. The stage is set. And what happens next is truly one of the greatest intellectual moments of the entire 20th century. It all came from this young Austrian logician, Kurt Gödel, and what he discovered would completely change how we think about truth itself. So back then, the big ultimate goal was something called Hilbert's program. The dream was to create one single formal system for all of mathematics that could do 2 things. One, it had to be complete, meaning it could prove any statement that was true. And 2, it had to be provably consistent, meaning you could use the system to prove that it would never, ever contradict itself. That was the holy grail. But then, in 1931, Gödel drops an absolute bombshell. It's called his first incompleteness theorem. And what he proved brilliantly was that for any logical system powerful enough to do basic arithmetic, there will always, always be statements that are true, but that you can never ever prove within that system. Just think about that. He proved that truth is bigger than proof. What's true is a bigger world than what we can prove is true. And if that wasn't mind-blowing enough, he followed it up with his second incompleteness theorem. This one showed that the other part of the dream, using math to prove that math is perfectly reliable, was also impossible. No system can prove its own consistency. So that whole quest for absolute, provable certainty, it was over. It turns out you just can't pull yourself up by your own logical bootstraps. But here's the crazy part. This wasn't a failure, not at all. Discovering these fundamental limits didn't kill mathematics. It actually supercharged it. This incredibly abstract journey into the limits of knowledge led directly to, well, the computer you're watching this on. Let's get into our final section and see how that happened. Okay, remember we talked about recursion theory, the field that asked, what is computable? Well, in the process of trying to define exactly what a step-by-step procedure even was, logicians like the amazing Alan Turing came up with the theoretical idea of a computer, a universal computing machine. They literally defined what computation is. They laid out the entire blueprint for computer science before the first electronic computer ever existed. These logicians were the secret architects of the digital age. And the impact is just everywhere. I mean, the very device you are watching this on right now, the software running it, the AI you might use, the databases that power the internet, all of it relies on the principles that were discovered during this incredibly deep, abstract search for the nature of mathematical truth. It's amazing. So we kind of end up back where we started, but with a much deeper understanding. The quest for absolute certainty didn't lead to a perfect final system. Instead, it showed us something way more profound. The map of what we can prove is never, ever going to be as big as the territory of what is actually true. And that reframes everything, right? Science and discovery aren't about finding one final answer anymore. It's about an infinite journey. There will always be new truths out there, just beyond the reach of our current logic, waiting to be discovered. So the real question is, what do you think that means for the future of what we can know?